So, very good morning one and all. I am Narayanan from INESC-MN Portugal, and I am glad in presenting you the paper on microfluidic ELISA for sensing prostate cancer biomarkers using integrated amorphous silicon photodiodes. So, today I would be guiding you through some introductory notes on prostate cancer and biomarkers that are specific to prostate cancer with special reference to PSA, and then talking about the microfluidic ELISA strategy that we are employing to read the PSA measurements, and then the photodiode as a detection mode. And then I would be describing some methodology about how we are going to do this, and then some results that would present the measurements on the PSA levels. And then I would summarize the results and then give you some future perspectives. Well, given the higher prevalence and incidence of prostate cancer, chances are that either we know somebody who has a prostate cancer or we have one. So, along these lines at this juncture, it becomes very significant that we strike a proper balance between the clinical ends and the biomedical technology. And for this, we use specific biomarkers which are obvious, and one such traditionally used biomarker is going to be prostate-specific antigen. And this PSA is very specific to the prostate gland, and these are synthesized by the epithelial cells that are lining the prostate glands, and they are secreted when these are elevated and when there is going to be a disruption in the architecture of the prostate cells. And when this is going to happen, the PSA is going to get increased in serum level, and it will be this PSA that we would be measuring to detect whether a person is going to be affected with prostate cancer or not. And for this, there are two types of PSAs that are commonly prevalent inside the human system. And one is going to be the free PSA, which is going to be very less when it's going to be incidentally in the system, and the other is going to be the complex PSA, which is going to be associated along with some protease inhibitors such as alpha-chymotrypsin. And for clever measurements, diagnostic methodologies now recommend the combined use of both free as well as complex PSA, which is called as measuring the method of percentage free PSA. And the clinical range for such measurements lie between 4 to 20 nanogram per milliliter in the blood, which is recognized as the targeted level for biomedical technologies that are aiming to develop the device for this. And over the recent years, the biomedical researchers have tried to apply and devise technologies for biomolecular detection that is going to be sometimes imposed by hard limits on physics and chemistry. For this, there needs to be a proper balance that needs to be established between various components when it comes to an interdisciplinary mode. And in such respect, we focus on microfabrication technology that is underlined by PDMS soft lithography, where we have aluminum hard mask, the patterns of which are transferred to an SU8 mold, and then we have a PDMS device which is used as a tool. And this tool of microfabricated PDMS device is employed to be performing a microfluidic assay. And this microfluidics, as most of us know, helps in a precise concentration of molecules both in space and time. And having had the tool and platform, we employ normal sandwich ELISA methodology to capture the molecule of interest and then detect it using the photodiodes, thus giving rise to the integrated biosensor. And focusing on the ELISA platform, what we are having will be two different sets of platform devices, which will be focusing one on free PSA capture and the other is going to be total PSA capture, that is going to majorly differ with the capture antibody that is going to take your target molecules. And for this, we have two different epitopes that are being targeted within the same antigens. And the detector molecule can be either tagged with a fluorophore or a chemiluminescent or colorimetric tag, because the photodiodes, as I will be showing very shortly, is able to measure in all these three modes of detection. And when we talk about the system optimization, it becomes indispensable when we are going to analyze a specific device for a biomolecular assay to check how long will it take for the preliminary molecules to come and bind to the surface of the sensor, and how many will eventually bind, and if at all everything binds, is it possible for us to extract everything from a dilute sample such as blood when it is going to be in the preliminary stages of a disease. And for this, one needs to start from operating with the surface chemistry, moving on to adjusting the microfluidic parameters, and also checking other relevant protocols like blocking, rinsing, specificity, cross-reactivity, etc. And for this sandwich ELISA system, we start with adsorbing the probe molecules on the surface, underlined by the passive adsorption method, which is simple and avoiding the complicated cross-linking protocols or other methodologies. And then we rinse away the unbound molecules to avoid false positive results, which is obvious. And then we flow the molecule or solution under analyte, which is going to be recognized. and then we remove again the non-specifically bind molecules and then detect it using the detector molecule. And then at last run the substrate if it's going to be either a chemiluminescent or a colorimetric mode of detection with the given parameters here. And our usual borderline lies between 0.5 microliter per minute for solutions under analysis, and then 5 microliter per minute with a stringent wash to remove non-specific binding under strict conditions. And then the amorphous silicon photodiodes that we are going to use is shown here in the cross-sectional anatomy, where you have a filter made of amorphous silicon carbide filter that is going to let your light only filtering the excitation light, and then we have the transparent ITO ear that is going to pass your light to the diode. And then these photodiodes have inherent advantages of having high quantum efficiencies, low dark currents, and then low temperature deposition, which is going to ease also its integration when it's going to come to a microfluidic integration with glass substrates and so on. And then here you see a chip that is carried in a photodiode chip that is carried in a chip carrier, and then you also see an optical micrograph of 200 by 200 device, which is going to be the array that we would be using as well. And then here we show the response of photon flux to the current density, and then we show a linear response here that is witnessed over a range of the flux that is going to be measured, and then also here you see the single molecule level until the surface saturation that's going to be reached. And then it becomes also important that we also look at the current methodologies that are available for the prostate cancer detection using the microfluidic modes. And we see that most of the methodologies that are being employed use an external detection device that somehow needs to be impregnated or implemented within the device system. So an integrated device assay methodology would be advantageous to avoid the shortcomings of using an external reader or coupling with a microscopic device like CLSM, for which we depend on sensitive, specific, and easy integrated approach like this, where the device that we have fabricated is slided over a printed circuit board that is connected to a picometer, and then we manually align here the microchannel to the array of photodiodes that we are going to read. And such integrated biosensing methodologies become advantageous when it has to go in for increasing the assay sensitivity with time, as well as for reproducibility measurements, both for signal acquisition and for analysis. And then here I showed the simple microchannel of the dimensions that we are going to use, upon which the microfluidic ELISA that I have already pointed out is being performed. And these detector molecules, as I showed, can be either a fluorescent or a chemiluminescent methodology to be implemented with these photodiodes. But one advantage of the chemiluminescent detection mode compared to the fluorescent or the colorimetric is that we can avoid an external light source. And it is this methodology that I would be showing very shortly, before which we see here a microscopic measurement of the fluorescent detection of the microfluidic ELISA performed. And then we see that though it shows an increase over a range, but then the clinical ranges still needs to be resolved. And for which, but this is a simple methodology where we capture the antigen between the two different antibodies, out of which one is going to be labeled. So obviously there needs to be a resolution of the signal in the clinically relevant range. And for the same measurements, we also show this fluorescent detection mode with photodiodes, as you see in the inset. But then, as you see here, this shows the same trend as that of the microscopic measurements we saw. When it comes to chemiluminescence, the resolution becomes a bit reliable. And then also the colorimetric detection shows the alignment of the microscopic and the photodiode readings. However, it would be desirable to have still a further resolution in the clinical range using yet another strategy that could be employed in the biological or the molecular recognition that we would be seeing now, for which we will be employing a biotin-avidin complex, because biotin-avidin is one of the strongest known interactions when it comes to a protein ligand. So the dissociation constant is of the order of 10 to the power of minus 15 molar. So what happens is, here we are going to use a biotinylated antibody that is going to detect the PSA. And this biotinylated antibody is going to be read by a labeled streptavidin, due to which there could be amplification that can be employed in the methodology. However, with a simple system with just one biotin-avidin interactions, it is still not possible to resolve the signal in the clinical range. And then we try to employ an amplification protocol using levels of avidin biotin. As you see here, the bigger labeled molecules, these are the biotinylated BSA molecules, which should be combined with the streptavidin, and then this streptavidin molecules again would be read by the other biotin and then recognized by the labeled streptavidin molecules. So such network of avidin biotin can give rise to amplification in the signal that we are desiring, and all the more the same system can also be used for capture methodology if one needs to intend the increase in the capturing of the analytes in very low complex molecules. So what happens here is we see then an increase in the resolution range with a range of 0 to 30 nanogram per ml that we were not able to achieve in the previous mode without the amplification. And this is the chemiluminescent mode. And here I also show the photodiode measurements, but with two different sets of antibodies. So the gray bars that you are going to see are one complete set of this experiment with a biotin-related antibody against epitope X, and then the black is going to be another one with biotin-related antibodies against epitope Y. And as we can see here, with a gray trend, we are able to see the increase in the amplitude, and with the black, we are able to resolve it even under lower levels. So now we are working on other sets of biotin-related antibodies, and our future perspective is to combine the advantage of both, where we are able to achieve both the amplitude as well as the increase in the resolution under lower limits. And to summarize, we have here the PSA used as a biomarker for microfluidic detection, and the parameters are optimized for sandwich assay. And then when this comes to amplification, we are indeed able to go near the clinical range and detect the lower levels of concentration of the PSA. And for future directions, we are going to focus on equimolar total PSA assays that were introduced during the introductory note, where one measures both the free as well as the complex forms of PSA, and then to calculate the relative surface coverage, because it becomes significant when it is going to talk about the surface properties, because it's a surface property that is going to ultimately cover the performance of a device as well as the transport of molecules from the bulk to the sensor surface. So this would be performed by microspotting experiments, and then we would also simultaneously try other PCA biomarkers such as microRNAs to have a multiplexing where we can read different biomarkers in the same device that would enhance the reliability of the diagnostic device that we are intended to develop. And then I acknowledge the members from INESC and also the ProSense team, which is EU FP7 Initial Training Network project on parallel diagnosis and detection of prostate cancer biomarkers. Thank you, and I'm happy to take questions.